Hello, mathematicians. Today, Kendall and I are going to be presenting section 5.3, in which we'll be looking at spherical harmonics and the general Dirichlet problem. Remember that a Dirichlet problem involves trying to solve Laplace's equation so that our solution satisfies some boundary condition on a particular region. Back in section 4.4, that region was the edge of a disk, and the solution involved expressing that boundary function as its Fourier series. The intuition here is that we can think of any 2π periodic function as wrapping around a circle, and therefore being defined on the circle. What we're going to do here is look at what happens when the surface for our boundary function is instead a sphere. It turns out that there's a similar family of functions called spherical harmonics that can form sort of a basis so that functions defined on a sphere can be written as a linear combination of these special functions. We've already seen Laplace's equation in spherical coordinates in section 5.1. Recall that r is our radial distance from the origin, theta is our polar angle, which you can think of as the co-latitude, that is π/2 minus the latitude, and phi is our azimuthal angle, which you can think of as the longitude. Our solution has to match up with the function f of theta and phi on the surface of our sphere. Now, we solved Laplace's equation using our usual method of separation of variables, and we ended up with three equations, one for r, one for phi, and one for theta. The first equation was a Cauchy-Euler equation, whose solutions were just simple powers of r. The second equation had our usual sine and cosine solutions, which we combined into a complex exponential. For the third equation, we needed to make a change of variables, s equals cosine theta, as well as its corresponding differential. Making this substitution, we ended up with what's called the associated Legendre differential equation. The solutions to this differential equation are the associated Legendre functions. Multiplying our solutions together, we found the product solutions to Laplace's equation. Let's take a closer look at these Legendre functions. They're explained in more full detail in sections 5.5 through 5.7, but we'll hit just enough of the highlights here to give you an intuition for how they work. Legendre's differential equation can be expressed generally as follows: 1 minus x squared times y double prime minus 2x times y prime plus mu times y equals 0, where x is between -1 and 1, and mu is some constant. We're interested in solutions that are bounded on the interval from -1 to 1, so we let mu be a non-negative integer of the form n times n plus 1. Then it can be shown using series that a special family of polynomials called Legendre polynomials solve this equation. These polynomials can be concisely defined using Rodriguez's formula. The nth Legendre polynomial is given by 1 over 2 to the n times n factorial times the nth derivative of the nth power of x squared minus 1. Let's look at the first few polynomials. The 0th Legendre polynomial is just the constant function 1, and the first Legendre polynomial is just the identity function x. After that, the second polynomial is 1/2 times the quantity 3x squared minus 1, and so on. Notice that the nth polynomial is of degree n, and that they alternate between being even functions and odd functions. If we look at the graphs, we can see that all of the polynomials pass through the point 1, 1, which means that the even ones pass through -1, 1, and the odd ones pass through -1, -1. What's more, these Legendre polynomials form an orthogonal set. If you integrate the product of any two Legendre polynomials over the interval from -1 to 1, you get 0 if the degrees are different, whereas if they match, you end up with 2 over 2n plus 1. Actually, this orthogonality should come as no surprise, since Legendre's equation is once again a special case of a regular Sturm-Liouville problem. In this case, the values of n times n plus 1 are the eigenvalues, and the Legendre polynomials are our eigenfunctions. So, as we saw in chapter 6, these eigenfunctions must be orthogonal. Once we've defined the Legendre polynomials, we can look at a related differential equation called the associated Legendre differential equation, which has an extra term of minus m squared over 1 minus x squared multiplied by the y. Notice that when m equals 0, we end up back at Legendre's differential equation. So the Legendre polynomials are still solutions to this associated equation. But for more general values of m, the solutions to this new differential equation are more generalized functions called the associated Legendre functions of order m, and are given by the formula Pnm of x equals -1 to the mth power times 1 minus x squared to the m over 2 power times the mth derivative of the nth Legendre polynomial. These functions are generalizations of Legendre polynomials. Note that since the 0th derivative of a function is just the function itself, the order 0 Legendre function is just a typical Legendre polynomial. We can also extend the definition to allow m to be negative, defining these associated Legendre functions as particular scalar multiples of their corresponding functions of positive order. This means that for any given value of n, we have a total of 2n plus 1 associated Legendre functions, whose orders range from -n to n. For any fixed m, the associated Legendre functions of order m also enjoy the same orthogonality relationships on the interval from -1 to 1, although this time we end up with an extra factor of n plus m factorial over n minus m factorial when the functions match. Now we're ready to define our spherical harmonics. For any non-negative integer n, and any integer m in the range from -n to n, we define the spherical harmonic Ynm as follows. We take the product of our complex exponential in phi with our associated Legendre polynomial of cosine theta, multiplied by a normalizing factor of the square root of 2n plus 1 over 4 pi times n minus m factorial over n plus m factorial. This coefficient makes it so that our spherical harmonics form an orthonormal set with respect to the weight function sine theta, which is part of the surface area element when working in spherical coordinates. Notice that when taking our inner product, we need to use the complex conjugate of our second function. This is usually the case when trying to define an inner product space over the complex numbers. Rather than being symmetric, our inner product has to be conjugate symmetric, or Hermitian. Otherwise, you could have a vector whose inner product with itself, the square of its norm, could turn out negative. Let's go ahead and verify this orthogonality relationship. Suppose we have two spherical harmonics, one with parameters n and m, and one with parameters n prime and m prime, and we put them into our inner product integral. First, let's expand the functions using the definition in terms of complex exponentials and associated Legendre functions. Then, we'll factor out those normalizing factors as some constant. We won't really need it yet. Now, since our spherical harmonics are multiplicatively separable functions, we can rewrite our integral as a product of an integral in phi and an integral in theta. For the first integral, we already know from section 2.6 that distinct complex exponentials are orthogonal. So if m and m prime don't match, then this integral comes out to 0. Now, suppose m and m prime do match. For the second integral, we can make the substitution x equals cosine theta. Then, we also know that distinct associated Legendre functions are orthogonal as long as they have the same m. So if n and n prime don't match, then the second integral comes out to 0. Thus, if we have two distinct spherical harmonics, their inner product is 0. Finally, what happens if m equals m prime and n equals n prime? Here we'll need that constant we've been ignoring, which, conveniently enough, now features the same factor twice, so we don't need that square root anymore. If we bring a 1 over 2 pi over to the first integral, then it evaluates to 1. Then, with the remaining integral, we can use the orthogonality relationship we saw earlier with the associated Legendre functions to show that once again we get 1. Thus, our set is orthonormal. By the way, stated another way, we know from complex variables that the product of Ynm and its complex conjugate is the square of its magnitude, so this integral comes out to 1 as well. To get a better feel for these spherical harmonics, we'd like to plot them in spherical coordinates, taking r as a function of theta and phi. However, keep in mind that these functions are actually complex valued. Our factor of e to the im phi can take on any value on the unit circle in the complex plane. So it could be real or imaginary, or anywhere in between. So if we want to be able to visualize these functions, we need to instead plot the modulus, that is the absolute value. But we can still retain the information of the argument, that is the angular phase, by coloring the surface, so that the hue corresponds to the argument. Real numbers are red when they're positive and cyan when they're negative. Imaginary numbers are lime green when they're positive and purple when they're negative. All the colors in between correspond to numbers that aren't purely real or purely imaginary. By the way, since our e to the im phi factor always has an absolute value of 1, that means that the modulus is independent of phi, and therefore the surfaces we get are rotationally symmetric about the z-axis. But by adding information about the phase back in using color, we can distinguish between graphs of positive and negative order harmonics. Looking at how the shapes evolve as n and m get larger and larger, you have to admit that there's some distinct beauty within these graphs and their relationships with each other. Now, if these sorts of shapes remind you of those pictures of atomic orbitals that you've seen in chemistry textbooks, well, you're actually on the right track. It turns out that those familiar orbital shapes are found by taking particular linear combinations of the positive and negative order harmonics, designed to cancel out the imaginary parts, much like when we write sines and cosines as linear combinations of complex exponential functions. That being said, the resulting orbital shapes aren't actually the exact regions where the electrons are contained. There's a non-zero chance that they can be found just about anywhere. But the shapes do still give us an idea of where an electron is most likely to be found, in sort of a vague probabilistic sense. Anyway, this process of taking linear combinations is exactly the purpose for which we developed these spherical harmonics in the first place. Just like functions defined on a circle can be written as a Fourier series of sines and cosines, functions defined on the surface of a sphere can be written as a spherical harmonic series expansion. We can represent our function f as a double summation, with n ranging from 0 to infinity, and then m ranging from negative n to n, of some coefficient times each of our spherical harmonics. That coefficient for any pair n-m is itself a double integral over the whole sphere, of our desired function times the complex conjugate of the corresponding spherical harmonic times our surface area element sine theta. That function f has to be square integrable, which means that the integral of the square of the absolute value of f times our surface area element over the whole sphere has to be a finite number. Also, f needs to be 2 pi periodic in phi, which is what lets us treat it as if it's a function of angular coordinates on a sphere. But if we meet these criteria, then spherical harmonics give us a way to represent functions on a sphere as linear combinations of these simple and independent components. If you want to get a better feel for what we looked at today, I've created a Maple file that lets you play with the Legendre polynomials, the associated Legendre functions, and the spherical harmonics. Maple has these functions built in. I've also included the calculations that give the orbital shapes. If you have any questions, let me know in the discussion board and I'll do my best to answer. For now, I'm going to leave you with Kendall, who will continue this line of thought to fully solve the Dirichlet problem in a ball using our spherical harmonics. Thank you.